Alright, in this video we're going to talk about calculating volumes of revolution using what's sometimes called the washer or disk method. So volumes of revolution, using disks or washers, and it's the same procedure. The disks and washer just kind of refers to somehow the object that's getting rotated about without going into too much theory on it. So the basic idea is this. So suppose we have our x and y axis. So x-axis, y-axis, and suppose we have some curve here, some function. We'll call it y equals f of x. And suppose we're going from the x-coordinate of A to the x-coordinate of B, and we're taking that region and we're rotating that. We'll go, in this case, about the x-axis. So we're going to rotate it here about the x-axis. This is going to make a three-dimensional object. You can kind of visualize this little region coming out and down. I won't try to do any artistry because I always mess it up. But again, you know, if you kind of think about this in three dimensions, maybe it's going to look like a vase, you know, if you imagine it on its side, or I don't know, it's going to look like some sort of object rotating about. And what we want to do is basically find the volume, the space trapped inside of that three-dimensional object. So there's two different ways to do these problems. Again, what we're going to use are called disks and washers. There's also a method called shells, which we'll also do an example of. And the other thing that's important here is the distinction between rotating about a horizontal line, like the x-axis. You can also rotate about a vertical line, say the y-axis. And I'm going to do some examples just rotating things about horizontal lines in this video. And then I'll also talk about rotating around vertical lines as well, using this disks and washer method. The basic formula, at least for this scenario, is your limits of integration come from the x-axis. Your limits of integration are going to be where the region starts to where it stops, so from A to B. And then you throw a pi in there, and then you take your function, and you square that. Okay, so in these videos I'm not going to do really much of the integration. I'm just going to talk about setting up. Usually the integration on these problems is relatively straightforward as far as integration goes. And one thing to notice too, if you were to rotate this region in the example I just gave, notice it's going to be a solid region. So just one little thing to kind of point out and to think about here. So let's do a specific example, again remembering this formula because that's going to be important. So usually you'll have a problem stated somehow like this at the beginning. So they'll say find the region bounded by maybe the x-axis, the y-axis, the line x equals 4 and y equals square root of x, and then they'll tell you some region to rotate it about. Alright, well usually in most of the problems, at least I've seen in most textbooks, you should be able to sketch out the graph. Graphing is one of those things that definitely some people are a little better at, some people are a little worse at. If you're taking a calculus class and you're at all shaky on graphing, I definitely encourage you to look over some basic graphs. It'll make life a lot easier for you, I believe. Okay, so anyway, back to this problem. So the x-axis, hey, we know that, the y-axis. I'm going to graph y equals square root of x first. And remember, y equals square root of x looks something like that. X equals 4 is a vertical line up and down. So I'm just going to generically put a line over here at x equals 4. So they're talking about this region being rotated about the x-axis. So I put a little arrow just to indicate where I'm twisting about. Okay, and I'm going to label this graph. I usually like to label things as I go. It makes things a little clearer for me. I don't have to look back at them. So again, looking at our formula from a second ago, it says, well, all really you have to do is think where the region starts, where it stops, whatever the function is, that's what goes inside of the formula and gets squared. Well, here the region starts at 0 and it stops at 4. So those are going to be my limits of integration from 0 to 4. Squeeze that in there. And then it says you throw a pi in there, and you could factor the pi out front because it's just a constant. So usually I go ahead and do that. It's easy to forget about it though, so don't forget about it. And then it says you take whatever your function is, in this case square root of x, and you square that thing. And that's it. So in this problem you would end up having to integrate the function from 0 to 4 of just x, since square root of x squared is just x. And again, in terms of integration, you're not going to get much easier than that. Okay? So you would find the antiderivative, x squared over 2, still remembering we have to multiply by pi out front, and then calculate that from 0 to 4. Okay, and get your final answer. And that number again would represent the volume of this original region being rotated about the x-axis. So you can kind of imagine in this example, if you rotate this region, it's going to kind of look like the tip of a bullet, to use a violent example, or maybe the bottom of a top or something like that. Okay, so that's the basic idea in these problems. So let's do one a little more complicated. Actually, we're going to do 3 more that are a little more complicated. Okay, so suppose now, our next example, we have the region bounded by the curves y equals square root of x and y equals x. And I'm going to do 3 different problems. I'm going to take this region, and the first one I'm going to rotate it about the x-axis. Part B, I'm going to rotate it about y equals -3. Again, notice this is a horizontal line. And in C, I'm going to rotate it about another horizontal line. Okay, and in general, I think it's good to think about this stuff in terms of the following. The formula is pi times, and I'm going to use what's called the outer radius squared. And you're going to subtract away the inner radius squared. And I'm going to try to make some more sense about what exactly I mean with this. Okay, so again, let's sketch our region. Y equals square root of x is something, again, kind of curvy. Again, it's coming down and it shouldn't, so forgive my bad graph. Y equals x is underneath here. Okay, so here's y equals square root of x, y equals x. So here we have to figure out the points of intersection. You can probably almost guess these, but suppose it was something more complicated. Again, to find points of intersection, you set them equal to each other. So I've got a y equals, so I can set square root of x equal to x. And to solve this, there's a few different ways you could do it. You could square both sides. If you square the left, you just get x. If you square the right, you get x squared. This is now a quadratic equation. To solve quadratic equations, we set them equal to 0 and either try to factor or use the quadratic formula. In this case, I can factor out an x, and I'm left with x minus 1 equals 0. And that tells me that either x equals 0 or x equals 1 are my points of intersection. If you weren't sure which graph was bigger over this region, what you could do is take a number between 0 and 1, say 1/2, let's make it even better, say 1/4, and plug it into the square root function, plug it into the x function, and see which one gives you a larger value. So if we use x equals 1/4, well, on the bottom one, y equals x, we'll just get y equals 1/4. If you use x equals 1/4 and you plug that into the square root function, the square root of 1/4 is 1/2. Well, 1/2 is bigger than 1/4. That means the square root function is bigger over this interval from 0 to 1. It's bigger than the function y equals x, so I know that y equals square root of x is bigger. So this is an important little idea. It's especially helpful if you can't graph the equations and you're not really sure what the functions look like. So think about what I just said here. It's really, I think, something if you can absorb this idea, it'll make things much easier for you. Okay, so we've got from 0 to 1. So let me use a different picture here. Let me clean it up before it gets too cluttered. Okay, so again, we've got our square root function on top, and it's trapped between that and y equals x, so it's just this little region. Again, we said y equals square root of x is on top, y equals x is on the bottom. We've got the limits of integration from 0 to 1. So already I know those are my limits of integration from 0 to 1. There's a pi in here, and now this is where we're going to use this idea of an outer radius and an inner radius. So what I mean by the outer radius is whatever line I'm rotating about, again we're rotating about the x-axis, I'm going to draw a line perpendicular to that line. It's going to hit my region, and right where it's going to stop, right before it leaves the region, that's what is considered the outer radius, so capital OR. Well, if you think about the height of this arrow, if you're at some generic x-coordinate, the height of it is going to be square root of x, and that's what we consider to be the outer radius. So the outer radius in this case is just going to be square root of x squared, and then we subtract away our inner radius, and we do the same thing. You just draw a line, whatever line you're rotating about, until you hit, till you just barely start to enter the region that you're rotating. Notice now I'm touching the curve y equals x. That's going to be my inner radius. So again, this is the inner radius. And it says, well, now I'm touching the graph of just x squared, and that's now the region, or excuse me, the integral that I have to calculate. And again, if you just square root of x, the square root of x squared is x minus x squared, and then you just do your normal integration. And that would be the setup for this region rotated about the x-axis. So let's take this same region and rotate it about the line y equals -3. Okay, so again, a similar idea. The only thing that's going to change here is going to be our outer and inner radius a little bit. Okay, so here's our graph of, again, y equals square root of x, y equals x. That hasn't changed at all. Our limits of integration are still going to be from 0 to 1. But now we're rotating about this line y equals -3, which is down here. Okay, so let's play this game again with the outer radius and the inner radius. So again, here's my region that I'm rotating. So again, whatever line I'm rotating about, I start right there, and I draw a line to my region, through my region, just until it stops. And again, that's going to be considered the outer radius. And then we do the same thing on the inside. So the line I'm rotating about, it's going to go, and just until you hit the region, that's going to be the inner radius. Okay, so again, now we have to calculate the lengths, basically, of those arrows, the outer radius and the inner radius arrow. Okay, so I've still got a pi. My limits of integration are still 0 to 1. Before, if you thought about the height of the arrow, when we were going about the x-axis, the height of the arrow was just the function you're touching, which is square root of x. Well, think about distances. How much further would you have to go down to get to this line? And don't be, thrown off by the fact that it says -3. Think about it in terms of a distance. Well, you would have to go another 3 units. So the length of this outer radius arrow is actually 3 plus the height, which comes from the function. So the outer radius is going to be 3 plus square root of x, quantity squared. And then you subtract away the inner radius. Well, again, from the x-axis to the line, y equals -3, that's a distance of 3. And then to get to the bottom part of my region, I would have to go up a height of x. So the inner radius is going to be 3 plus x, quantity squared. And again, that's now the integral that represents this region being rotated about y equals negative 3. And that's the basic idea. So again, a little confusing the first time you do this stuff. But I think if you start thinking about problems in terms of this, hopefully they'll get a little bit easier as you go. Again, to integrate this thing, the only thing I would do is just multiply this out. 3 plus square root of x times 3 plus square root of x. I would have 3 plus x times 3 plus x. So you'd have to do quite a bit of multiplying, collecting like terms. But then, again, the integration should be relatively straightforward. Alright, so last but not least, let's take this same region and go about the line y equals 8. Okay, so the same idea, except now the horizontal line I'm rotating about is going to be, well, it's going to be above the region. So here's y equals square root of x again, y equals x. And now the region I'm rotating about is going to be above it. So here is the line y equals 8. Okay, and now I'm going to do the same thing. I'm going to think about an outer radius and an inner radius. And this one's, I think, probably the most tricky of all of them. My limits of integration are still the same. It's still from 0 to 1. I still have my pi out front. Whoops, sorry, had a little camera malfunction there. Alright, sorry about that. Don't have the most advanced studio here, so you'll have to bear with me a little bit. Alright, so again, the outer radius. The line I'm rotating here is about y equals 8. So the same thing as before. Whatever line I'm rotating about, I start from there. Okay, I go until I just hit my region, and again, right before I leave the region, that's going to be my outer radius. So again, I'll abbreviate it OR. My inner radius is going to be from the line until just where I'm about to start hitting the region. So that'll be my inner radius. Okay, so let's think about, again, the lengths of these arrows. Okay, well, if you think about this little height, this is just the height of the curve y equals x. Well, the length from the line, the height from y equals 8 to the x-axis is 8 units. But obviously that arrow doesn't go all the way down, so it's not 8 units long. It's 8 units less a little bit. Well, how much am I subtracting off? The amount I'm subtracting off comes from the function y equals x. So the outer radius is going to be 8, but I have to subtract off a little bit, namely x, because that's the curve I'm touching. And then I subtract away the inner radius, and now I do the same thing. The whole height, whoops, is a length of 8, but I'm not going all the way down. I have to subtract off basically the top function that I'm touching, which is now the square root function. Again, this is a really horrible graph. The square root looks like it's coming down, and it shouldn't be. So let me maybe move it over a little bit. Well, the inner radius now, it's going to be 8 minus basically the top function that I'm touching, which is square root of x, quantity squared. And that's now the integral that represents the volume of this region, now getting rotated about this horizontal line, y equals 8. Okay, so again, this being the outer radius, this being the inner radius. So again, a little confusing, but again, I think if you start thinking about stuff in terms of outer and inner radiuses, it'll get a little bit clearer. And also, too, notice if you're rotating it about the x or y axis, we didn't really talk about the y axis yet, but about the x axis, you don't have to subtract really anything off. There was no outer radius or inner radius, at least for, well, I should be even more careful. That's not true at all. What I meant to say is, when you're rotating about the x-axis, Where'd my example go? I've misplaced them all. Basically, here we go. When you're rotating about the x-axis, you don't have to really manipulate the functions at all. You still have to think about which one's the outer, which one's the inner, but notice you're just using one and the other. If you work this problem out and you find that you get a negative number, well, volumes can never be negative, so what that means is, most likely, you just got these your two functions backwards. Of course, it could mean that you did something a little more dramatically incorrect, but that would be the first place I would look, is maybe I've just got my outer radius and inner radius mixed up. When you're rotating about something that's not the x-axis, or we'll see the y-axis as well, notice then we have to take our functions, we had square root of x and x, and then tweak them a little bit. We add on these constants, maybe 3 plus that, 3 plus that, or as in my last example, we had 8 minus and 8 minus. So again, I think if you can start thinking about these things, look at them in terms of outer radiuses and inner radiuses, you'll see that actually these problems become a little more systematic. Again, the one place that will really give people, I think most people, problems is just being able to simply graph them in the first place. So if that's what's getting you, definitely review your graphing and this stuff will get a lot easier for you. Again, feel free to visit my website. I'm going to have some more videos on there as well about rotating about the y-axis or a vertical line. Likewise, I'll do these examples also using the shell method.